All right. Yeah, thanks, Rale. So I'm taking up here. And indeed, as Rale mentioned, we will be covering a bunch of different methods which try to work at intersections between learning-based approaches and more mathematical optimization-based methods. We thought it could be a good idea to give a quick primer on reinforcement learning. So taking a step back from the problem that Rale just introduced and think a little bit about general key concepts and terminology so that we have this in place for future talks in this tutorial. And of course, we have very little time to do this. So just by no means we will be able to discuss things in detail, but hopefully this will be enough to kind of guide you and give at least the terminology for you to kind of follow what will come in the next talk. And just as a sort of reference, here are some suggested resources that we definitely advise you to check out, both in terms of books and also online classes if you're more into a dynamic kind of learning approach. But so that being said, what is reinforcement learning and what way do we mean by it? And fundamentally, reinforcement learning can be seen as a mathematical formalism for learning-based decision-making. So, and in particular, it is an approach for learning-based decision-making where we try to learn to do so from experience, whereby success is essentially measured by a reward metric, which signifies how good or how bad a specific action was in a specific state. And slightly more formally, reinforcement learning typically entails an interaction loop between an agent A, which takes some kind of action into the environment, the pictorial world here on the right of the slide. And this action somehow influences the evolution of the environment, whatever we think that is for the specific problem at hand. And this action then leads the environment to basically give us back a new updated state, which is influenced by this action, and a reward metric, which indeed measures how good that action was in that specific state. And if you see this kind of looping over time, we essentially have this trajectory, tau, which is referred to here on the slide, which is essentially a sequence of states in action over time here until an end of this kind of experience determined by H, where H may be infinite, if we're considering kind of continual learning scenarios. And in practice, reinforcement learning is typically formulated within a Markov decision process, here referred to as calligraphic M on the slide. And the Markov decision process is nothing else than a tuple, which essentially is comprised by a state space S, which essentially represents the space of all possible states our system could be in. An action space A, graphic A, which represents a set of all possible actions that our agent could take in the environment. Dynamics function P, which represents how the system evolved or the environment evolves given an action that we take in a specific state. And in particular, here on the slide, we're representing this dynamics function as a probability distribution over next states. So you see here P of ST plus 1 given ST AT. The fourth element is the reward function R, which is a reward that maps from a state and an action to a scalar value, which represents this measure of performance. And last but not least, a discount factor, which essentially is a value between 0 and 1, which is used to signify how much we care about short-term reward against long-term reward. And hoping that this setting is clear, the overall goal of reinforcement learning is typically to learn a policy, which we represent by pi, which expresses a distribution over actions given states, here represented by as pi of AT given ST, such that we maximize this specific objective function represented on the slide, which is essentially the expected sum of cumulative reward, where this expectation is considered under the trajectory distribution induced by the policy. And I will repeat this in a different way. By trajectory distribution, we mean the distribution of all possible trajectories tau that we could observe by running our policy in the environment. For example, to make this concrete, specific policy pi could be expressed as a parametric function, pi theta, with parameters theta. And this essentially translates this problem into an optimization problem where we want to pick the value of these parameters, theta, such that we maximize this objective function. Any questions here? Great. So let's make this a little bit more concrete with some examples. We are looking at Markov decision processes, which again are represented by this tuple of elements. For example, if we consider the game of chess, the state space could be the set of all possible positions of the board. The action space could be the next move that our agent or our player can do in that specific state. The dynamics in this case are deterministic in the sense that given a specific move that I do in a specific configuration of the board, this leads to a deterministic next state of the board. And the reward function in this case, again, it's up to the user, but it could be something as simple as +1 if we win the game, -1 if we lose the game. And a second example in the context of autonomous driving could be, again, where we want to drive a car autonomously. The state space could be represented by all the possible sensor reading we get from the car. So this could be camera images, LiDARs, other sensors. The action space could be the steering angle or the throttle, for example, if we are assuming they're controlling the car. The dynamics in this case could be stochastic at some level of abstraction, whereby it is hard to deterministically predict where the car will end up in future time. And the reward function, if we are assuming we want to win like a specific race, this could be the average speed of the ego vehicle over the circuit, for example. But again, hopefully this kind of made the terminology a little bit more concrete. And one might ask, okay, given all of these new terminology, why should we care about reinforcement learning? And the idea here, kind of simply put, is that this abstracts away a lot of the complexities that might be representing real-world problems, in the sense that reinforcement learning at its core is a methodology where, to some level, we have to specify a reward function, and then the agent is tasked with learning basically everything else. And obviously, this reinforcement learning has been extremely successful over the last years, ranging from board games to robotics to more lately, even the alignment of large language models such as ChatGPT. And it's indeed kind of an area of extremely intense research in the ML community. And if we compare reinforcement learning to other machine learning areas, RL has some kind of redeeming characteristics. First of all, if you kind of think back at what we've been saying so far, nowhere we have been discussing about a formal teacher showing us explicitly what is the correct action to take, right? The only thing that guides learning is the reward signal. So if you compare to standard, say, supervised learning, we don't have a teacher that tells us what to do in a specific scenario. We just have some kind of abstract reward function which tells us how good something is. A second characteristic is that in this case, or in specific scenarios, feedback from the environment may be delayed. Again, consider the case of chess. It is hard to give us credit to a specific move in a specific instant of the game until we actually reach the end of the game, right? So in this case, feedback might be very, very delayed until we reach the end of the game. And this obviously creates some problem in kind of assigning credit for how good a specific action was for the overall outcome. A third characteristic is that data, as it is probably obvious, is not IID in the case of reinforcement learning. It is quite the opposite, because the given actions that we take highly influence the following states that we will see in our environment. And so this is in strong contrast with general theory in learning and statistical learning theory, whereby an underlying assumption for many learning-based methods is that data is actually IID, or identically distributed. So hoping that this is clear, I think it is important to spend a few words on the concept of value functions, because it is kind of a key concept throughout the entire RL landscape. And in particular, it is very often useful to know what is the value of a state. And we have different definitions of value, of course. We could think of state values, which then are embedded into state value functions. And a state value is essentially the expected total reward that we expect to see if we start in that state and act accordingly to some policy. So if you want to see it in math, the value function is indeed this expectation, again, over all the possible trajectories that we could see in the environment of the sum of rewards that we have starting from the state onwards. And again, now abstracting away from the math, it is kind of an intuitive value which represents more or less kind of how much reward do I expect to gain when I'm in a specific state. And this is an extremely useful quantity to then base our decision-making upon. A second definition of value is the action state value, which very much like the state value, then kind of adds an extra dimension, which is the one of the actions. And specifically, again, the action state value function, Q, represents the expected total reward we expect to have in the future, starting from a state and taking an action in that state. And this obviously has some differences when developing specific reinforcement learning algorithms. But value functions and Q functions are indeed key concepts in RL methodology. And a key result that drives many algorithms out there is based on the principle of optimality, which essentially allows us to basically show that value functions obey special self-consistency equations known as Bellman equations. And these essentially say that value functions can be decomposed in the reward that we obtain in a specific time t plus the value of the next state. This is extremely useful and follows the principles of dynamic programming because it basically allows us to decompose the problem in time while allowing us to optimize only for a one-step look ahead through the use of the value function itself. And again, I'm aware that this is a lot of content in a very short time, but it is, I think, important that that we fixate these concepts because indeed a lot of RL literature is based upon these ideas here. And if we talk about RL, there are a bunch of different algorithms. Obviously, a big categorization is whether these are model-free or model-based, whereby the main difference is that whether we want to use some knowledge of the dynamics or not. So model-free algorithms do not use the dynamics, so just assume we don't know and we don't even care about learning them. Model-based methods, on the other hand, either rely on some known approximations or actually try to learn a model of the dynamics. Within model-free algorithms, there is a further categorization, which is policy optimization methods opposed to value-based methods. Where in policy optimization, we directly optimize the RL objective, meaning we try to find that optimal values of those parameters theta to maximize the objective, while in value-based methods, the policy is implicitly defined through value functions. While on the other hand, for model-based methods, as I was saying, we could either attempt to learn the model and then do something with it, or we are given the model and then we can simply optimize over it in a sense. But this is, again, a quick fly-through key concepts in RL, hopefully giving you a little bit of an overview of the different methods that are out there, specifically for, we will see in the next talks for AMOD coordination. But for what relates with this tutorial, we will mostly focus on policy optimization methods. How are we doing with time? Okay. Any questions? Because this is the last slide for this set. Yes.
So what we experience is that it will create some sort of oscillation like there. So for example, if you're trying to use the controller and learn the speed, it will give you some sort of preservation. So what is the
Yeah, I will repeat the question and correct me if I misunderstood. But you're basically saying RL in some cases assumes you have a stochastic policy, which, for example, if the policy is choosing the speed of a vehicle, this might be stochastic, and so this means that there could be some oscillation around your overall decision. Does this summarize? Yeah, and you are correct. But the point is that in reinforcement learning, the choice of the policy is actually up to the designer, right? You could choose a stochastic policy, which essentially means we learn a policy pi of theta that basically go back to this. That basically samples from all the possible space of velocities, for example. Or you could learn a deterministic policy, which on the other hand, given a state, outputs a single value for the velocity, right? So in RL, typically there's this distinction between stochastic policies and deterministic policies. On the other hand, if your policy is stochastic, say you learn a Gaussian distribution over velocity, then you could always have like an inference scheme that picks a specific value of the velocity, say the mode or the mean of your distribution, right? Therefore, yes, you have stochasticity in your representation of the policy, but at test time, which is what you care about, you obviously do not want to sample, right? You do not want to take details of the distribution, but rather kind of exploit your current knowledge, if that makes sense. It is a good point because it touches on the problem of exploration, right? And I will repeat the question. You were saying if we go for deterministic policy, we won't be exploring enough while we learn, I guess. At the end of the day, it boils down to there are specific exploration strategies which might fit well deterministic policies. For example, if you're familiar with Q-learning as an algorithm, the policy is in itself deterministic, right? Because you're picking the argmax of your Q function. But during training time, as a typical exploration strategy is the epsilon greedy strategy, which basically samples randomly from your space of actions epsilon% of the times, which basically allows you to explore while learning a deterministic policy, right? So kind of putting all together, the problem with stochastic policies, kind of I follow what you're saying, but I think at the end of the day, it really boils down to the specific strategy that you apply either during the training phase or during the kind of inference phase, if that makes sense. Whereby even if the policy is stochastic, you could actually behave deterministically. Yes.
I would ask about, you mentioned the example of ChatGPT.
Mm-hmm.
If you can tell us more about how they're.
Yeah. Sure. I mean, kind of the secret sauce is obviously worth millions and billions of dollars, so I won't be able to say exactly what they do. But at the high level, they learn reward function or a reward model, which is essentially trying to estimate how good a specific response is from the chatbot. So say you are a human being, you receive a response from ChatGPT. It is hard to evaluate kind of how good or how bad the specific response is, right? It's probably easier to kind of rank different options. And so what they do is that they have kind of a pre-trained large language model, which is trained on like plethora, like the internet of text. And then what they want to use RL for is for the fine-tuning phase, meaning given this pre-trained model that can generate text that is plausibly real, we then want to fine-tune it such that it is a good chatbot. And so what they do is that they learn a reward model which approximates kind of a scalar measure of how good the response is. And if this reward metric is actually accurate enough, then you can optimize over it through RL. Does this answer your question? And did not repeat the question, but the question is, can you tell us more about ChatGPT alignment? Awesome, great. I think we're also good with time.
Yes.
So now that we have kind of we flew through kind of an introduction to reinforcement learning. Now, where we talked about large language models and just abstract systems, let's try to make this more concrete in the context of what Joelle was presenting before. So the coordination of autonomous mobility on demand systems. So the outline for this talk is that we will kind of quickly fly through again the AMOD coordination problem. And then we will introduce kind of foundational concepts of this methodology, which we call graph reinforcement learning, specifically around two main blocks. The first one is the policy structure. So we will kind of describe a policy structure that allows us to leverage the best of both worlds between machine learning, specifically reinforcement learning, and optimization-based methods. And then in the second block, we will be looking at specifically policy representations, whereby we leverage the fact that the transportation network is a network, and therefore we can use neural networks that specifically are better tailored for graph-based problems. And then we'll go through some case studies and general discussion. Okay, so as Joelle was mentioning before, AMOD coordination in practice entails three, four decision points. The first one is dispatching, that is assigning vehicles to customers that request for transportation. The second one is rebalancing, that is for all those vehicles that are not requesting for transportation, we need to choose where to have them roam, ideally to anticipate future demand. And the third one, in this case, so Joelle was referring to routing. We are, in this slide, we're looking at specifically charging as an additional dimension in the case that the fleet of vehicles you're considering is an electrical fleet of vehicles. And what is really important is that these decisions, in order to be actually useful for real-world operators, need to be made, first of all, in real time and at scale, right? Which is really what is a problem here. Because these systems and kind of taking decisions over these systems for real-world systems can scale very badly with the dimensionality of the transportation network. And if we look at state-of-the-art approaches in AMOD coordinations, these typically fall within one of three categories. The first one is heuristics, which, if on one hand, these are kind of simple to implement, fairly reliable, and also efficient computationally, these are typically suboptimal because they introduce some simplification to the overall problem. A second class of methods is optimization-based methods. For example, approaches that attempt to solve a network flow problem over a space, charge, time graph, whereby we could map a transportation network into a graph, whereby nodes could represent areas in the region, and the edges, the connectivity between these areas. And the goal there is choosing the flow of vehicles over the edges of this graph. And once you have this representation of the AMOD system, then optimizing over the system essentially entails picking the flow, here represented by Xij and Yij, to differentiate between dispatching flow and rebalancing flow over these edges of the graph. And within these methods, these are obviously extremely high performance because if you're able to solve this problem and the problem kind of successfully represents your system, then you're typically guaranteed to have a good enough solution if the computation times allows it. But this is exactly the point, because these methods typically do not scale well with the dimensionality of the network, right? So you could have very good solutions, but then scaling up these methods to real-world scale is challenging. A third class of methods is learning-based approaches, which on the other hand are extremely efficient because typically once trained, kind of computing an action entails a forward pass in a neural network, for example. And are also pretty good with handling stochasticities, which on the other hand could be complicated for optimization-based methods, where you would have to rely on, say, stochastic optimization. But the kind of big downsides of learning-based methods is the performance guarantee. So there is really nothing that enforces some guarantee of the quality of the solution or even getting to a meaningful solution once we have a learning-based, especially if it's black box-based methods like neural networks. And so with this work, what we do is that we develop a framework that leverages or attempts to leverage the best of both worlds between learning-based approaches and optimization-based methods. And now we will see in the next slides how we attempt to do so. Okay, and so as I was mentioning, we'll go through kind of these two main blocks. The first one is discussing policy structure that enables us to kind of combine optimization-based methods and learning-based methods. And then we'll look at policy representation. So when kind of discussing graph reinforcement learning, this typically entails a three-step framework, whereby the instantaneous decision that we have to take at time t, where kind of, let's remember that the decision for us entails picking a flow over the edges of a graph. We decompose this decision into this three-step framework. In the first step, we solve passenger matching for a given time t by solving a convex problem here on the slide, but without going into the math. Is essentially a linear program that assigns available vehicles to passengers in order to maximize, for example, total profit for the operator. So in the step one, we are basically solving the dispatching problem at an instant, a specific time t. The step two entails using a learned behavior policy pi, as we were referring to before. In this case, let us assume that this is learned for now. We will then look how we learn this policy. But this behavior policy pi in step two is essentially tasked with computing the desired distribution of idle vehicles that we would like to see in the future. And kind of let me rephrase this for clarity. So step one handles with dispatching. So we are assigning vehicles to customers. In step two and three together, we are solving rebalancing in this case. That is assigning, well, kind of having vehicles roam in the system without explicitly being matched with a customer. And we do this dividing this rebalancing problem in two steps. In the first step, we choose what is or reinforcement learning here gives us a desired allocation of vehicles that we would like to have in the system. In step three, what we do is we convert this distribution into actionable flows by solving another linear program. Again, this is only for time t. Where, again, without going into the details of the math, but at a high level, what this linear program is doing is essentially trying to give us the flows over the edges of this graph, which achieve as best as possible the desired distribution of vehicles, which we computed in step two. Any questions at this point? Okay. And so again, kind of to put things together, we have this overall problem of AMOD coordination, which we can see as a network flow problem that is given a graph representation of the system. Coordinating an AMOD fleet can be seen as choosing the flow of vehicles over edges in the graph. This network flow problem we choose to decompose in a three-step process, whereby we first assign vehicles to customers, solving dispatching, and then in a two-step procedure where we first compute a desired allocation of vehicles over the kind of spatially over the grid. And then we try to achieve this as best as possible by solving a linear program that maps this desired distribution into flows. Okay. So why is this interesting? This specific formulation, as we will see also in the next talks, has some redeeming properties. And specifically here, I'm kind of abstracting away from the specific formulation by seeing the two steps that entail rebalancing as reinforcement learning, tasked with specifying a desired next state in our environment. In this case, for us, the next state is a desired allocation of vehicles. And then we try to achieve this desired next state by solving a linear control problem, which, broadly speaking, attempts to minimize a measure of distance d between the state that reinforcement learning predicted and the state that we would actually obtain if we were to do some actions in the system. And this decomposition has some appealing properties. First of all, if we only look at reinforcement learning or like policy that represents decision-making over edges, we are extremely simplifying the problem for reinforcement learning, because rather than defining a distribution over all possible flows on the graph, we're specifying a distribution over nodes, which is a much smaller dimension, typically. In terms of scalability, this kind of is actually extremely fast at inference time, because once the agent is trained, evaluating the RL policy entails taking a forward step in a neural net, so extremely fast. And solving the second step is actually a linear program, so also extremely fast. On the other hand, if we look at learning-based approaches, we were saying before how one of the drawbacks is guaranteeing performance or safety of the system from the output of the learning system. In this case, we actually could see step 2 as a safety filters that essentially maps what reinforcement learning is saying to something that satisfies some constraints that the user might specify. And this could be, is actually quite handy in dealing with out-of-distribution scenarios, for example. And last but not least, is actually one of the key advantages of this, in my opinion, is that this overall framework decomposes the problem in time. So if you think back at what we were saying in the previous slide, in no way we were saying that the decision was looking at future states of the system or future like expected states of the system. On the other hand, we were only solving immediate kind of problems at time t. And the reason why this decomposition would actually works in this case is because we are leveraging the fact that reinforcement learning, so step 2 in the 3-step process, is actually learned to maximize expected reward over time. So this is a property of reinforcement learning in general. You're learning instantaneous policy, which at time t gives you an action. But this action is learned, or this policy is learned under the problem of trying to maximize the cumulative reward over time. So in a way, we exploit exact optimization when it is useful to, for example, enforce constraints, have high guarantees of quality instantaneously. But then we push the impacts of stochasticity, kind of temporal dimension, or nonlinearity over time by the fact that we're using reinforcement learning in the loop. Yes.
What happens if the LPT does not be exactly at the entire stage? So we try to get a growth at all.
Yeah, exactly. So this is a good point. So the question is, what happens if step 2, so the linear control problem, does not lead to a feasible solution, or at least does not match the solution, the state that step 1 is giving? It is a good question. And the point is that this is actually why we care about step 2. The point is that we have kind of currently no kind of proven way of guaranteeing that the state that the learning-based agent provides is even feasible. On the other hand, we have extremely good ways of guaranteeing feasibility with standard optimization techniques. And so the point here is that even if the state might not be feasible, the optimization is constructed to try to achieve it as best as it can, but then it will always prioritize feasibility to kind of achieving that state, if that makes sense. Yes, this is a good point. So the question is, if we do not achieve the state that reinforcement learning was giving us, how do we pass this back to the RL for the next decision? The point is that RL, at the end of the day, is only learning a mapping from a current state of the system to an action. By design, the state of the system is always feasible because it's what's happening in reality, right? So what happens in practice is that RL will give us a desired state. We could either achieve it or not, but regardless, step 2 will give us a feasible flow, a feasible action to take. And this feasible action leads to a state that is feasible, right? So RL doesn't really care, now to kind of wrap the answer back. RL doesn't really care that we achieve this state or not. It only cares that it receives an input, a state as input back from the system. How do we train? We will come to this later. There are different ways of training. For now, you could assume a standard reinforcement learning pipeline whereby we interact with the system over time. We leave the agent take decisions, observe the environment reactions, and loop over time, if that makes sense. So if you have like a mobility simulator, you could have your agent coordinate a fleet. This RL will initially say pretty random things at the beginning because it's randomly initialized, but then over time it will learn to adjust its desired state to kind of maximize whatever reward metric you're specifying. Does it make sense? Yeah. Yes. Yeah, so until now, and we will come to this later in this talk and also in future, in later talks, we did not talk about learning at all. We are just describing the structure of the policy, right? So in here, in no way I was discussing interaction with the environment, and you're very correct. Here we were just describing what is our policy, what does our policy even look like? In practice, again, as I was answering before, you could imagine, if it kind of helps for understanding, that this policy is embedded within a traditional RL scheme where you have a simulation that is happening and you're kind of iteratively using your policy to take decision, observe the outputs and rewards, take another decision, observe again the reward, and so forth. Yeah. And I think there was, yeah. Yeah, so the question is, how do we train the policy if we do not know the desired distribution? So if you recall what we were discussing in the previous kind of RL introduction, we were saying that reinforcement learning in general is a learning paradigm that does not need an explicit teacher. So it doesn't need someone to actually tell it what a good distribution is. It will just try distributions. And then by observing the consequences of choosing one distribution or the other, it will kind of automatically adjust to select the best distribution, if that makes sense. Yeah. Yes. Yeah, it's a good question. So the question is, how do we handle multi-criteria decision making? At the end of the day, I feel it comes to how you specify the reward function, right? So again, kind of a nice thing, and at the same time, maybe a drawback of RL is that reward definition matters a lot in determining the overall behavior of the policy that we learn. And so if our behavior cares about multiple objectives, we should encode them in the reward function. So shortly put, if you have multiple objectives that you care about, you should inform your reward definition about these multiple objectives, and then you optimize for it. Yeah. Yes. Just 1 second. How are we doing with time? Okay. Yes. We'll take a couple more.
And it's kind of, in my opinion, kind of preparing for the future. But in step one, the decision making is very myopic. You're just doing matching the passenger with vehicles right now. And would it be beneficial, or is it going to be a limitation if you, for example, batching of passengers? So, for example, you let passenger wait for like a few minutes to do the batching of passengers.
Yeah.
Or is it going to be a limitation?
Yeah, it's a good question. So the question is, in step 2 and 3, kind of we do care about future state implicitly through RL, but in step 1, we're actually solving this instantaneous problem. Is very correct. I would say the nice thing about this framework is that this is completely kind of agnostic to the specific formulations of step 1 and step 3, right? So if we had something smarter or something tailored for a specific application that we want to include in step 1, there's nothing that really stops us in doing so. So if you want to include a batch of customers altogether, you could obviously do that in step 1. If you want to have something that has some kind of planning horizon rather than just instantaneous planning, you could do that. So this is fairly agnostic to the specific formulations of 1 and 3. What really matters is that step 2, which is RL, will implicitly learn to adapt its output depending on what step 1 and 3 are. Okay. So going to the second block. So until now we discussed the policy structure. So we were saying we want to learn this policy for AMOD coordination. How does it have to look like? And we discussed this 3-step framework. Now we slightly switch gears and we discuss, okay, we want this policy to output a desired distribution of vehicles. What does this policy need to look like? What is this function that maps from states to desired distribution? And the key observation here is that transportation networks obviously are naturally represented as graphs, where, for example, nodes represent areas in the city and edges the connectivity between them. And the point here is that graph neural networks, which is a specific kind of architecture of neural networks, pair naturally with the techniques that are often used in transportation literature, because it is a specific architecture designed to work with network like graph structured inputs and outputs. And the reasons why graph neural networks, we think, pair naturally with the kind of computations that we have to do in these scenarios, it's because of 2 key properties that these have. The first one is permutation invariance, which we'll go in a second. And the second one is the fact that graph neural networks are essentially a functional class that is non-parametric with respect to the topology of the network. But we'll see more in a moment. So the bottom line is transportation networks are not represented as graphs. Graph neural networks are designed to operate as graphs. Sounds like a win-win. So what do we mean by permutation invariance? So assume we have a specific network representation of our city, where again, nodes represent areas and edges the connectivity between them. We could foresee kind of, if you want, naive approach to this problem is using a standard multi-layer perceptron as the neural net architecture that maps from states to decisions. And if we were to do this, we could foresee something where we have specific information over each node, here represented by these colored block diagrams. And in order to be able to even concretely pass this into a multi-layer perceptron, we would have to essentially unroll the graph into a big vector and feed it to a feed-forward neural network and observe the output. The point is that this unrolling the graph into a vector is kind of an operation that is not permutation invariant. Specifically, if we were to simply kind of redesign the network or simply switch the name of nodes, we would have obtained a completely different input for the neural network. And you see how this is a property that doesn't really make sense intuitively, because just by the fact that we are calling nodes differently, it doesn't really change the kind of the properties or the characteristics of the graph itself. Ideally, we would want a functional class that is invariant to these permutations. The second problem that we would observe if we were to use standard feed-forward neural networks with graph-based architectures is the fact that these are naturally linked to a specific topology of the network, not only the permutation, but even just the, for example, number of nodes. So again, if we were to consider that example where we unroll the features over nodes into a long vector, now say we train this, everything works beautifully, and now we want to, for example, extend our system to a new area, right? The point is that standard multi-layer perceptions would simply not be able to tackle this case because they have been trained on a specific input dimension, right? And you see that this is not, again, a good property that we would ideally desire from our neural network. Kind of to remedy to this, kind of graph convolutions are specifically interesting formulations because they define an operator that essentially convolutes over nodes in the graphs or over elements in the graph more generally. So you could see learning a specific mapping that does not consider the graph as an unrolled vector, but rather is a function that convolutes node by node over the graph aggregate all the information, and then gives us an output at the end. And indeed, if you think about, again, this is obviously high level, but if you think about what we were describing here, the fact that we have convolution over graph elements essentially gives us these two properties that we were referring to before. If our overall function is based on aggregating information from a convolution operator over nodes, it will be independent or invariant to the fact that we are relabeling nodes in the graph. And at the same time, if we add one new node, one or more new nodes in the graph, the same function will still apply because we're still convoluting over nodes in the graph. Yes. Sorry, so the question is the input dimension of, I believe you're referring to this case, does not depend on the number of nodes, but only on the features. You're referring to the multi-layer perceptron specifically? It depends what features you have, right? So if your features are not linked to the nodes, so if you have global features that represent your network, then I would agree with you. If, on the other hand, you have specific nodes that are related, the specific features that are related to a node, say the node represents an area and the features represent the number of requests in that area, I would argue, and let me know what you think, but I would argue that this isn't inherently tied with the number of nodes that we have on the graph. Does it make sense? Okay. Okay. And so we discussed these two main blocks, policy structure. So what does the policy look like? And given the structure, what does the specific mapping from state to actions look like? In all of this, as some of you were referring during questions, we never touched kind of learning signal or learning strategies. And the reason why we did not touch it is because we kind of designed this framework in mind to be as agnostic as possible to the learning scheme, right? So we could see this as, we could see the policy being learned through online reinforcement learning. We could see this learned through other types of reinforcement learning, such as meta reinforcement learning or offline reinforcement learning, or even through something like imitation learning or behavior cloning, right? So this overall scheme doesn't really care about how we get the gradients for the parameters of our policy. We are just describing our overall framework, so the structure and the representation, but we don't really care how we get the gradients. We could get these through RL or through supervised learning. Kind of this holds regardless. And I guess I will quickly go through some empirical analysis just to relax for a second. So as we were discussing before, the overall design and framework we have for experiments, at least in the online reinforcement learning case, is that we assume we have some trip travel data, which we can use to calibrate some sort of simulator of mobility. We can use this simulator then as an environment for our learning agent to interact with. And once we have a trained agent, we can then deploy it into, for example, a novel instance of that same simulator and observe the results. So this is at a high level, the kind of interaction that we are referring to. And here I'll just, again, mention a few kind of high level takeaways. Again, probably the specific results are not that important, but I think the takeaways is something I want to make sure I pass by. So in general, we try to benchmark these methods to a number of different baselines belonging to the three main categories we were discussing before. So optimization-based, heuristics, and learning-based. We typically like to compare our methods to an oracle method, which basically represents, assume we have perfect information about the system, all future events, unlimited computational budget. What is the kind of solution that we will get there? So we have an upper bound of performance. We obviously have like more realistic implementation of that same method, kind of learning-based methods and heuristics. And here we were looking at two specific scenarios, one for San Francisco and one for New York, where in this case, we were solving even the charging problem. So the problem is defined by a number of nodes that represent the area, a number of charging levels that we also want to consider. And so here, the second column, 5 to 20, represents like macro areas in the transportation network. So how many areas we're considering. And I would say the kind of main takeaway here is that here we are only taking the perspective of the system operator. If we compare results of optimization-based, learning-based, and heuristics, we see generally a scheme where the learning-based component, so the graph RL we were discussing, typically matches the performance of optimization-based methods, kind of across levels. But while also bringing kind of a substantial benefit in computational efficiency. So we were saying that one of the drawbacks of purely optimization-based methods is scaling to large dimensions. The fact that we are using this policy structure that decomposes problem in time is pretty fast at testing, because taking a decision only entails a forward pass in the neural net. We basically get a picture where kind of we are typically able to match the performance of optimization-based methods, while basically guaranteeing kind of the same computational efficiency of heuristics. And I would say another key takeaway is probably the transfer capabilities of these methods. So because we were using graph neural nets as a policy structure, we discussed how these are invariant to permutations and how these could potentially work on where we talk about service expansion of adding nodes to the graph. It turns out that if we train a network on a subgraph and then deploy the same network on, say, a full version or extended version of that graph, kind of the similar functional mapping exhibits some interesting transfer performance, kind of hinting at the fact that there could be some interesting level of training on a small network that is fast to evaluate, fast to simulate, and then deploy this gradually into larger and larger networks. Okay, and so kind of to summarize, so we presented kind of this graph reinforcement learning framework for AMOD coordination. Here we were looking at these three decision-making aspects: dispatching, rebalancing, and charging. Crucially, at the end, we are saying that GraphRL could represent, or at least be some ideas that represent ways of putting together the benefits of learning-based and optimization-based methods for these problems. And we saw how this also these methods demonstrate some promising transfer and generalization capability. If we talk about like service area expansion or even across cities. Okay, so this is my last slide. Any questions? Happy to take questions. Yeah. Yes. Yes, the main idea there, if we are good with time, so just a quick answer. It relates with the fact that we're using graph neural networks. So the standard neural network is actually something that maps from a predefined input vector to a predefined output vector. Graph neural nets is something that defines a convolution operator over graph elements. And so we have something that kind of iteratively loops over, say, nodes in the graph, and then aggregates all the information from these different sequential operations and outputs something at the end. And by the fact that we have this convolution, this is independent, or at least is invariant to the number of nodes in the graph. Yeah, thanks. And I think probably we don't have time for questions. I'm happy to take them offline. Yeah, thanks.